Well, good evening, everyone. Thank you all for joining us here today for ASBN's take on 3-minute thesis towards sustainable and circular economy. My name's Marina, and I'll be your MC for the night. Before we begin, I would like to begin with an acknowledgement of country. Today, we gather on the ancestral lands of the Kaurna people, and we wish to acknowledge them as the traditional owners. The Adelaide Sustainable Building Network respect their enduring relationship with these lands and waters and honor their rich cultural heritage. It is upon these lands that Uniting Communities stands. And as we delve into topics of sustainability and circular economy, we are inspired by the traditional sustainable practices of the Kaurna people. Now, before we dive into our discussion that I'm sure you're all looking forward to, I'd just like to get some housekeeping items out of the way. Firstly, please ensure your mobiles are turned to silent to give our speakers the best chance at presenting their research. Bathrooms are located outside the hall, straight down and to the right. And we definitely encourage participation in today's discussions, but please wait for all the presentations to end, and then we'll invite you to speak and ask your questions. Now, we've got an exciting format lined up for today. It's based on the 3-minute thesis style presentations, where each presenter will have 3 minutes to present their research summarized. And the idea is to give them a chance to concisely, which can be difficult, but is exciting, present their research, and then give you all a chance to engage in a panel discussion with each of them around the topics of sustainability and moving towards a circular economy in the built environment. So these researchers vary all the way from first year PhD all the way through to senior lecturer. So you're going to get a variety of the research that's available at the University of Adelaide in the area. And I look forward to a lively discussion. And without further ado, I will present the first speaker. So let's welcome our first speaker, Ricardo Leonard. He's a PhD candidate at the University of Adelaide with a background as a practicing architect, currently advancing sustainable design through his research on self-shading steel facade components and their potential to enhance energy efficiency and minimize waste through industry collaboration. I'll hand over to Ricardo.
Good evening, everyone. So I'm a first-year PhD student, and my project title is Self-Shading Steel Envelopes for Commercial Buildings in Warm to Hot Climates. And self-shading is one of a recognized strategy to reduce the heat gain that comes to the building envelope. It works by blocking a certain portion of solar radiations that comes to the building surfaces. So although there's an increasing interest in the research of self-shading, the use of steel material remain unexplored, largely unexplored, especially in the current literature. So BlueScope Building Components, together with Adelaide University, are embarking on this project to actually bridge those gaps. And as you can see here, there's a imaginary BlueScope building surrounded by heritage-style buildings and modern buildings covered with glasses. And you can see that there's the BlueScope buildings are using a modular facade with overlapping shadows. And people might think that they're just seeing some kind of a regular modern style building, but there's something more to it. So if you can see here, there's a guy working on the design and optimizations, and actually this guy trying to conduct market research. They try to see what are the products there on the market, and then try to see what are the thermal performance of the products, and they try to make an optimized version of it. And not just an optimized version, but also an alternative versions of that products. And then the product's going to go through a prototyping and validation phase where the product's going to be tested in the real life situations. And to ensure that the results from the optimization actually in lines with what's happened in the real life situations. And then the product's going to move to a productions and mobilization phase. And in this case, depending on the shape of the products, it's going to utilize the regular cold roll forming machine, which the product's going to be precisely cut. And the product is not just going to be a precise product, but it should be something that's going to minimize the waste productions during the process. And after that, it's going to go through the applications in walling and roofing because it's an envelopes. And this project's aims and targeted two minimum aims. The first aim is to create a self-shaded envelope to reduce the heat gain that comes to the building, which eventually is going to reduce the heat gain and also increase the energy efficiency that comes into the buildings. And the second one is the modular system actually try to facilitate the easier some kind of maintenance whenever necessary. Thank you.
Take a seat, Ricardo. Thank you, Ricardo, for opening up the presentations with an interesting self-shading perspective. Next up, we have another materials presentation. Come on, technology. We have, please join me in welcoming our second speaker, Lloyd. He's a passionate civil and structural engineer and PhD candidate at the University of Adelaide. And he's looking at, he does a unique blend of academic and consulting roles and is looking at accelerating the transition towards a sustainable built environment by researching transitioning the concrete industry through circular economy, through optimization of multi-generation recycled aggregate concrete. So I move on to a different material and welcome Lloyd.
Thank you, Marina. Oh. It's a good one, isn't it? Lovely. All right, it's 3. Perfect. All right. Thank you, Marina, for introducing me. As she said, my name is Lloyd. I'm a civil and structural engineer and current PhD candidate in civil and environmental engineering at the University of Adelaide. Today, I'll present to you my PhD on transitioning the concrete industry to a circular economy through optimization of multi-generation recycled aggregate concrete. So the optimization of multi-generation concrete is something I'm really, really passionate about. Now, the reason for this is because it's really critical, and I think that it's going to have a global impact, not just locally in Adelaide. So to start off, concrete is the most used manufactured material on Earth. And by volume consists of around 70% aggregate. On top of this, aggregate is the second most consumed natural resource on Earth, second only to water. And in concrete with 70% aggregate, we find that there's no surprise that it is an industry leader in both construction demolition waste and natural resource depletion. The circular economy, a regenerative system aimed at minimizing waste and maximizing resource efficiency, presents an interesting opportunity to address this challenge. To embrace the circular economy in the concrete industry, we must develop sustainable practices for utilizing recycled material. My research focuses on multi-generation recycled aggregate concrete, which involves using concrete waste as a source of recycled aggregate in subsequent generations. This approach reduces the demand for virgin aggregate in waste and reduces the demand for virgin aggregate and diverts waste from landfills. To assess the feasibility and performance of multi-generation recycled aggregate concrete, we conducted the world's largest experimental program to date. This experimental program was conducted over 4 generations of recycling. At each generation, we attempted to change mix designs and optimize the performance of the concrete that resulted. On top of this, links between varying aggregate properties and the performance of the concrete were determined. We found that changing different aspects of the mix design could maintain concrete performance indefinitely throughout the generations. This also enabled the potential for informed mix design to maybe be adopted in the industry later on. This experimental program also outlined the changes to design that will need to occur so that multi-generation recycled aggregate concrete can be used for higher order products, such as reinforced concrete. In addition to the experimental study, a comprehensive model was developed to assess the circularity of different concrete mix designs. This model takes into account the whole life cycle of concrete, including the resources used, environmental impact, energy consumption, and product performance. By quantifying circularity, industry and academia can compare and select the most sustainable mix designs. In conclusion, my research represents a significant step towards transitioning the concrete industry towards a circular economy. By optimizing concrete mix design for multi-generation recycled aggregate concrete, we can minimize waste, reduce environmental impact, and conserve valuable resources. The large-scale experimental study combined with the circular economy assessment model provides a solid foundation for sustainable concrete production. Through the implementation of these findings, we can contribute to a more sustainable future, one where the concrete industry operates in harmony with the principles of circular economy. I'm hopeful that my research will inspire further adoption of these practices, accelerating the transition towards a greener, more efficient concrete industry. Thank you.
Thank you, Lloyd. I'll now welcome our third speaker, Daniel Rossetto, who's a professional in global carbon markets, finance and energy transition and industrial decarbonization, who's leveraging his international experience to conduct research on legislative initiatives for sustainable building materials as part of his doctoral thesis at the University of Adelaide. So, welcome, Daniel.
Thank you. Well, thank you to the network for this invitation to share details of my research. I explore carbon market mechanisms and the incentives they create for circular solutions. And there are four main pillars to my research of relevance to the circular economy and sustainability more broadly. The first considers the emergence of the nationally determined contributions for mitigating climate change that arise under the Paris Agreement, and the shift away from the top-down approach that was used in the Kyoto Protocol to the Paris Agreement. Australia, for example, has set a 43% reduction under its nationally determined contribution by 2030, whereas a country like, or a region like the EU has a target of 55%. So there's differentiation. Developing countries are not required to move as quickly because of a principle known as common but differentiated responsibilities that's used under the UN Climate Change Convention. Laudable as this may seem, countries moving at different speeds on emission reduction, as implied by common but differentiated responsibilities, risks impacting the competitiveness of emissions-intensive products that are traded across international borders. The most affected products are, funnily enough, commonly used building materials such as steel, also concrete, and in fact aluminium are the most energy intensive and emissions intensive in many cases materials in the world. So the third pillar of my research looks at some of the measures that are being used by countries to actually mitigate carbon leakage risk. And there are new drivers leading to proposals and regulatory reforms that move away from the free allocation systems that have been very popular towards what we call border carbon mechanisms, which is essentially like a border carbon tax. International trade and sovereignty implications arise, and the issues, it's fair to say, have not been fully resolved at the international level. The counter view, of course, is that these measures are in fact industrial protectionism, just in a slightly different form. So therefore, under the final pillar of my research, I consider the downstream opportunity that arises, particularly in the built environment. And notwithstanding the turbulence, the very development of border carbon mechanisms is driving a very strong interest in firm-specific and even factory-specific embodied energy and emissions information. And the incentives that are connected to the national and international mechanisms that will encourage collaboration between the users of the emissions-intensive materials and in fact the specifiers of those materials, as well as the producers. So we can go into that in a little bit more detail during the Q&A. But these opportunities are new. They represent a shift in the incentives that can support the development of sustainable buildings. So thank you very much for your attention, and I look forward to the discussion.
Thank you, Daniel. Next up, we've got Dr. Larissa Martins, who's going to give a different angle to sustainability research. So we're zooming a bit out of the circular economy perspective and looking at sustainability in terms of well-being. Dr. Larissa Arakawa Martins is a postdoctoral research fellow at the University of Adelaide, employing data analysis and machine learning for predictive modeling to improve individualized thermal comfort, particularly for older people. Welcome, Larissa.
My presentation might be a little bit different from the others. Hopefully it's not too far out. Okay, so this is my slide. I'm just going to start with a little anecdote about my research and why I started researching older people, their housing, and sustainability related to that. So since I was little, I have always been fascinated with the notion of time. And I found it so interesting that one of my pastimes was watching Back to the Future and also trying to synchronize all the clocks in my house exactly 5 minutes late, just like in the opening scene of this movie. And the more I thought about the passage of time and the notion of time, the more interested I got about what it all meant, which resulted in a fascination to the most universal and famous phase of time, which is aging. And I always thought, how old will I live? Will I age fast? And more importantly, will I age well? This brought me to my PhD thesis, which I completed last year. And this is the topic. So the only difference is that instead of focusing on the speed at which time passes, I wanted to focus on the quality of this passage. So recent research shows that as we all age, biological changes affect the our thermal perception, and also sensitivity, which makes us more vulnerable as we age to extremes in temperatures in our environments, like the common cold spells and heat waves we have in Australia. And with populations aging all around the world, it becomes timely to better understand older people's thermal needs and preferences so that comfort in our homes is maximized and also healthy aging is achieved and sustainability is improved. However, the problem is that the complex changes that affect our bodies throughout the aging process, they don't happen the same way to everybody. We experience aging in different speeds and intensities, which results in an older population that is very diverse. So we can't generalize it. And it's like imagining that unlike the synchronized clocks back in my house, every person's biological clock ticks in a different way. Therefore, predicting how people, and older people specifically, would feel inside an environment is very difficult. And to be able to predict it accurately, we need to look deeply into what makes people different and what makes our houses different, and also what makes our houses more sustainable. To do that, myself and a group of researchers, we monitored more than 70 older people throughout South Australia in more or less 50 houses. And we monitored not only their thermal preferences throughout 9 months, but also how their houses performed, what made them different. We also measured body measurements, quality of life, and also health status. And with that data and the help of machine learning, and unfortunately not a time machine, I was able to create mathematical models that can predict personalized thermal comfort predictions depending on the conditions of the homes and also the different people's unique characteristics. And in the future, what I would like to research a little bit more, and that's what I'm actually doing for my postdoc, is try to use and apply these comfort models, personalized comfort models, to fully capture people's diversity so we can use them to design smart buildings. These models can also assist caretakers and healthcare providers with information to monitor and match older people's and patients in their environments and their homes to their individual needs. And by making houses more comfortable, more efficient, and more sustainable for our future needs, I always like to say that instead of a synonym of running out of time, aging or older age will become the time of our lives. That's it.
Thank you kindly, Larissa, for that perspective. And now we're going to end with our final speaker, rounding out the discussion, Dr. Ehsan Sharifi. Dr. Ehsan Sharifi is a senior lecturer at the University of Adelaide, and his research focuses on microclimates, urban microclimates, leveraging impacts of climates for a healthier and low-carbon urban living to explore the mitigation of carbon emissions through green urban spaces within the context of Adelaide. So, welcome, Ehsan.
I saw the other slides and I'm feeling embarrassed to put so many graphs in here. So we love trees, aren't we? So the main effect is that they do stabilize their stormwater when it's too stormy and rainy, and the other is that they purify air for us to breathe, oxygen, and they absorb carbon dioxide. But they have some sweet side effects as well. They're not side effects, but they're very sweet to us because they cool the microclimate as well. So since 2014, we did have multiple projects on the cooling impacts of the trees for the urban microclimate in different scales. And the main idea behind it was that when we have a better thermal comfort during the summer, specifically in cities with temperate climate like Adelaide, we will be encouraged to get more outdoors. And by doing that, we're going to use less air conditioning. And that will drive the carbon emissions reduction. So the main concept was here, increase the outdoor thermal comfort and getting into a low carbon living. So in a sense for trees, it's a kind of a sweet side effect. It's not the real reason we plant them. But basically what we did, we monitored the cooling effects in different suburbs, and we compared that with the temperatures, annual temperatures, monthly temperatures, daily temperatures of those suburbs along South Australia for years, since 2014. And we put them in some analysis formats, and we figure out that their impact of the trees, the cooling impact of the trees, is quite different in summer and winter. In fact, there are a lot of claims that, well, what about the penalty of the winter cooling? And what we figure out that the penalty of winter cooling is 2 or 3 times less than the cooling effect of the trees for the summer. So that's the first thing we figure out. Then we put it against the climate change scenarios for 2030 and 2090 for the RCP 4.5, which is a medium emission scenario, which means that we're going to reduce the carbon emissions slightly, but not dramatically. And that will predict for the winter and summer temperature in Australia, in South Australia, we're anticipating 0.6 and 1.6 degrees temperature increase. So we put the information that we got from different suburbs with different amount of greenery, the temperature differences against the climate change scenarios for 2030 and 2090. And what we figure out here is that, I mean, this is the existing scenario here, scenario 1, which means that summer, winter, both 0.6 degrees warmer, and 2090, both of them 1.6 degrees warmer. I mean, in terms of the thermal comfort, you might claim that, oh, look, 1.6 degrees, what is it? 0.6 degrees, I might not even feel that. But when we get to the energy consumption, the equation is a bit different. So when we get to the scenario 2, which is a moderate scenario, come on. We get to the moderate scenario, which is the existing scenario is what we have, like a CBD of Adelaide, imagine that. So we have around 15% of greenery at the moment. Some say 25% because we count parklands in there. It's a kind of a fake count. We shouldn't count them in the City of Adelaide greenery ratio. But the scenario 2, which was the target of the 2020 project, gives 20% of greenery and 30% of permeable surfaces, and the rest of that is roads and buildings in those. So that scenario will give us some kind of counter measuring the climate change changes by 2030, but still in 2090, it's not effective. We've got to experience around the degree of increase. Scenario 3, which is 30% greenery, is what we have in the city of Burnside right now. We have more of that in Mitcham and in Only councils right now. So if we get to that and 30% of the permeable surfaces, we didn't increase that in the scenario because there are so much you can do permeable. So roads, if they get permeable, there are some issues with that as well. So we count the backyards and walkways, pathways, if we turn them into permeable surfaces, and 40% as they are roads and buildings. We don't want it to be permeable or green. We can, but we don't count as a let's say, a widespread greenery in there. So with that scenario, we can definitely countermeasure the summer, 2.4 degrees, we can bring it down. And again, that's based on what we see in the spaces. This is not based on simulation or modeling or anything. It's just the suburbs compared to each other. So we are not talking about the crazy greenery. 30% greenery around my house look like this. It's not crazy greenery that we can't achieve. So how it's affecting energy consumption, that's an interesting part. So if you see here, we have the temperature ranges, and for each degree, how much the energy demand changes. And if you look at here, 8 degrees to 23 degrees, we have almost like a very lying bed here. And where do we have more than 28 degrees, we have a very steep rise. So where are we in Adelaide? You rarely get less than 8 degrees. So we are mostly in here. So when we start cooling down the space, we are really going to affect the summer energy consumption right here. So calculated to be around 100 kilograms of carbon emissions per person by 2030 and 70 kilograms of carbon per person, like it's the weight of a person of carbon per person per year for Adelaide, if we do that increase in 3 canopies. That's about it. I think I went over 3 minutes.
Thank you, Ihsan, and thank you for all of your presentations today. You're clearly showcasing a commitment to researching innovative ways to advance sustainability and circular economy principles within the built environment. For this next part of the presentations, I will be joining the panel, and I'll open with asking you a question, and then after that, we invite you all to either ask an individual question, ask the panel a question, and we'll see how that goes. So, the question to start our discussion is, can each of you briefly describe how the implementation of your research would transform the built environment in terms of achieving sustainability and/or circular economy goals? Maybe just in one sentence, however you prefer.
Go in a row.
So actually what I'm trying to do is to build a product that can be used in the earlier design phase, especially in the architectural industry. So because architecture usually emphasize more on the aesthetic aspect, so why not bringing sustainability right in front of them? That's it.
I've determined a range of methods that industry can employ to use to categorize recycled aggregate that they've achieved and received from multiple different areas. Once they've categorized that aggregate, it can determine a mixed design for any properties that they determine, and they'll then be able to achieve the mixed design that gives them the desired properties to achieve an appropriate high order of recycled concrete that can be used for high order products.
And I think in terms of these incentive mechanisms that I mentioned before, we might have, for example, an environmental product declaration for a particular product which includes already 15 or 20% of recycled material in that product. And there might be a supplier of those materials that has an alternative product which actually has maybe 50%, but it's slightly more expensive. And as a result of the, say for example, in Australia, we have the new reformed safeguard mechanism. There are opportunities for, if the project is able to deliver an emission reduction through having this higher level of recycled content, there is actually, in theory, a way to monetize the environmental benefit and offset the capital cost difference that exists between the product with the 20% recycled content versus the 50%. So it equalizes the capital cost penalties on some of these more circular solutions in theory. Whether it turns out to work like that in practice remains to be seen, but I think the opportunity is being built and exists for entrepreneurial flair within the market, to find and to exploit.
I think, thinking about my research specifically, I think by making our houses more sustainable and also more comfortable for the future, I think the word here is resilience. So we are making it, we're living longer, we're living healthier, and our buildings are also performing much better for a longer period of time. It's resilience also to future climate. We do live in an era of this discussion on climate change or changing climate. And it's important to think how our buildings are going to live longer and more sustainable. So in a way, understanding our needs in our homes will make our buildings live longer, and we will live longer and healthier.
For me, I like trees, and I like everything that comes with them. animals and birds and everything. So what I'm trying to do in the research, and also when I'm talking to people, is to show them that the things that we are talking about are not crazy far away, but the window for doing them are going to be closed. So a tree going to take 15 years to grow. So when we talk about 2030 in 2016, that was 14 years ago, and now it's 7 years, 7 days later. So the tree might not get mature in 7 years. And when we go ahead, these targets going to be pushed away and away. So they are achievable. And there are other methods as well. It's not just, we don't say cooling the city with the trees because it looks cool, because we want to live with them and because we need them and they need us. So I'm trying to show that in a kind of a end user oriented, tools that practitioners can use, policymakers can decide, rather than having large scale claims about this percentage in the whole city council, go and implement that, and people don't know what to do. So I'm trying to make it more practical. Yeah.
Thank you, all of you. I like how even though the research was completely different fields of study, we're bringing it back to this: how do we improve the future of the built environment and the sustainability of where we live. I would like to open to questions. So that was a lot of content, and I'm sure you've got some questions. I can see some hands ready to be raised. So if you could raise your hand, we'll just call on you for your questions. You could either address individual researchers or the panel. There we go.
Gentleman in the middle. So there's, as I understand it, with the carbon market, if you are a big company and you want to purchase carbon credits to become carbon neutral, there are only two methods to purchase them that are certified at the moment, which is woodlots and returning farming land back to native veg. Are there any more that you're looking at?
I mean, in Australia, there are many more. So those two methods, yes. So basically, there are maybe at the moment 8 or 9 different categories of methods, which include, of all things, energy efficiency in residential or commercial buildings can, in theory, generate the credits that can be used under the safeguard mechanism. Plus, since the reforms have been passed in March in Australia, we're now actually opening up. The Commonwealth Government policy is now to allow bottom-up proposals of methodology. So if you think you have a really good way of reducing emissions, you can actually propose it. So it's definitely not limited to just the two methods.
So for example, if you say grew hemp and then you process that and put it into a house as an internal wall envelope, and that wall envelope took up 50 kilos of CO2, 105 kilos of CO2 per square metre over 50 years, you could get a credit on a credit plus growing the hemp. You put carbon in the soil, and then you put carbon in the plant, and then the building absorbs carbon for 50 years. Have you heard of that one before?
Not of that specific one. However, biosequestration is a very common, with any species, there is a degree of understanding of how much sequestration different species contribute. And if that is scientifically justifiable and can be verified, then the Commonwealth are open, to accrediting those types of projects.
I've also heard about if you recycle building material from a building and put it into a new one, you can have a zero carbon input for that recycled material. Have you heard that?
Yeah, I mean, there are definitely.
So if you've got the carbon, if you're say measuring the carbon miles that go into a building, if you recycle the material, the carbon footprint is very low.
Yeah, although one of the things which actually just came out in the Advertiser this morning, which is very interesting, was that the Lord Mayor has raised the topic of adaptive reuse of sort of older, lower grade office buildings in Adelaide. And there were some developers this morning in the Advertiser saying, this is too expensive, but what I would like to highlight is that in addition to all the recycled content that one could put into new building materials, which is wonderful and ought to be explored, let's not also forget the CO2 savings and the broader environmental savings that one can achieve through adaptive reuse of these types of strategies, which, okay, there might be an economic constraint, like the developers were saying this morning, but I think, that's where we can work together, to find an economic as well as, technical solution to those sorts of problems. Correct, yes.
Thank you for starting off that conversation. We've got Yara. Would you like to ask a question?
Thank you for your beautiful presentations. You just said the magic word, which is exactly what I was very excited. My favorite topic at the moment. However, I'm also very fond of circular economy. And I do have a question for Lloyd about the model of circular economy. Obviously, the last thing you want to do is recycle.
Yes.
That's the last option.
Yep.
Have you also looked at other options as part of your research about deconstruct and things like that?
Yep. So obviously, maintaining a structure as it is and repurposing that building at the end of its life for another cause is the optimum solution when we're talking about circular economy. And yes, recycling is down the bottom end of that scale in circular economy. However, my research aims at maintaining the performance of that concrete over the recycling generations. So maintaining performance and maintaining it at the same level of performance that it came from is an important aspect of reaching a circular economy milestone. On top of that, we can recycle 100% of the retained concrete. So all the concrete that we are able to recover can be recycled. Some of that is going to be recycled in ways that aren't the best. So when we crush it up, we get coarse aggregate, which we can recycle. And my research has shown that we can repurpose that at a higher order. But there's some fines that are produced in that recycling process, and they're not good in concrete. So they really degrade the quality. So we can't use them as sands. Now, those fines can be turned into cement again. So they can be heated up. We're then burning off the CO2 again. But we're not causing a demand for natural resources, natural limestone, that we would then heat up and turn into cement in the first place. So it's not a perfect case scenario, but it's kind of the best case scenario we can get at this point in time. The best strategies is lowering the cement content and stuff like that in the mix design. So our best method of approaching a circular economy with recycling of concrete is with the materials we currently have for cement and stuff like that, is just reducing the cement content, optimizing mix design to maintain performance, and looking at supplementary materials that can lower the CO2 related to the cements that we've used, or the binders that we've used, and also perform at a higher standard. So it's really about maintaining a high standard of work to keep a circular economy in use. Yeah.
Thank you for that. Looking for questions? Ken?
Ricardo, I'd like to ask you a little bit about your steel research, and especially anything in regards to metal or steel in fabrication, or especially on a surface level. People will be talking about thermal bridging. So could you give us a little bit of insight around how, if your research does go into understanding thermal bridging performance, not just like the self-shading benefits or modular benefits, and if so, what are some cool things that might be coming our way?
Yeah, so basically what I'm trying to focus right now is just the envelope. So in every steel panel or steel sandwich panel, they have some kind of connections, sockets, and it can produce a thermal bridging. So what I'm trying to focus now is just to how to make this self-shaded area reduce the heat gain that comes to the building envelope. And after that, there's also a probability that we're gonna try different types of assembly that can reduce the thermal bridging. That doesn't have to penetrate the building. So it's like a plug and play where you can just plug the module and then you can just kind of replace it. But we haven't gone into more detailed research about how plug and play works. And yeah, that's one of the one of the avenue that we're just probably going to pursue in the future.
Thanks.
Yeah,
Please go
just
ahead.
maybe on that notion of, got a couple of questions actually, if you don't mind. So, just with the seal thermal capture on buildings and cooling of buildings, are there consequences in terms of how that may, if you do reflection on urban heat islands, like sort of raised the way, which is great to have that sort of in mind.
Yeah.
So, are there sort of consequences with that in terms of outside the building? So, urban heat, reflection by an external environment.
So in a steel material, usually we have some kind of coating with different solar absorption. So basically, what we are using is a blue scoop steel with a coating with the solar absorption ranging from 0.35 to 0.7. So it all depends on the color that we want to apply to the facade as well as the roughness. So yeah, just the roughness and the color can affect everything. Can affect the reflections, can affect the urban heat island. So yeah, there might be some interesting study about how it can reflect and how it affects the urban heat island.
Did you want to add to that?
Can I?
also,
Yeah, I want to
Ian?
say something about that. So you imagine a normal steel facade with some ribs on the facade that shade over the other parts. So, and there is a thermal bridging behind that. So there is a steel profile behind that that will transfer the heat inside the building. In a general sense, when you have the building and you have the sun and the sun shines and it absorbs the energy, and at night it's going to give it back. So the whole system in a daily cycle is in balance, but it's the matter of how much of it we let in when, and how much of it we reflect when. So with detailing, we can fix that. So if we provide shade with the self-shading facade over when we have the thermal bridging, then you have less concentrated heat on that specific spot, letting less energy to get into the building. So this is the work of our architect usually. What we see in the practice is that we get the steel facades done by whoever is being able to screw them in the facade, not designing with an architect, or even if they are designed, nobody feel any pressure to put them in the same style or in the same size as specified. And that's a problem with the workmanship. It can be done. It's not a crazy idea. It's just a matter of I have shade here and I do want the connection to be exactly on that spot because I want shade over that spot, which is the profile behind it.
Thank you. I might come back to other questions. There's two more. Paul, I think you had one, and then I'll come to the front.
Just in relation to concrete, I'm just curious as to, who you're working with in terms of producers and where it sits in terms of commercialization.
So at the moment, I'm not working with an industry partner for my recycled aggregate research. So my hope is that once my work is published in a full set, that I will be able to provide a model for the industry, and that will be spread over the full industry scope. Obviously, it's best if this can be applied, all over the world. My models, my experimental work will be probably the most critical. So that, because it's explored a range of experiments that no one else has done at this stage, it's showing the full range of scatter that we'll expect to see in the real industry and in a real world scenario. That means that other researchers in the future can look at it and go, look, this is what we've got. This is how we can design our mixed designs in another country where they're using other aggregate to suit a multi-generation recycled aggregate concrete. Here in Adelaide, I believe that once my work is published, businesses will be able to take it up as soon as it is published. We have done our work on the aggregates commonly used in Adelaide. We have done it on mixed designs that are commonly used in industry, optimizing as many performances as possible. And I believe that if the confidence is there, which it will be from my research, it's definitely available. The main area that I think is going to limit it is that there are going to need to be design changes in order to use it. So I can maintain mechanical performance across all the generations. I can maintain some durability factors, but there is particular problems with shrinkage. It's not out of the question though in terms of design. So with relative design changes, there will be the ability to apply this to a real world scenario. So we're talking about changes to the Australian standards where the capacity reduction factors are altered. These are very simple changes, and I will suggest these changes in my final reports. But that's the main hurdle I think that we need to get over before it's used. Apart from that, based on the research, an engineer could certify a project at the moment and design outside the scope of the Australian standards for particular designs. Some recycled aggregate concretes, particularly first generations and stuff like that, the shrinkage isn't going to be a problem, and we can design just as we would with normal concrete. So yeah, I do think that if industry confidence is brought up and there's enough exposure to it, we'll see it used within a couple of years.
The steel shading panels, I don't understand correctly, but presumably their effect is to really reflect heat because they're not absorbing it and retaining it. So it seems to me that as a result, the ambient temperature in the daytime around the buildings could be a bit higher, but at night time it could be lower because that heat hasn't been absorbed by the buildings. I'm just wondering if there's any reflections on the impacts from that diurnal change, if there was a lot of this shading in particular city.
Yeah, basically what the goal of the self-shading is actually to reduce the heat gain through the shadows, through the shaded area. And there is also a lot of things that can happen in the self-shading facade. So for example, if you are using like some kind of a cavity between the actual buildings, the actual wall of the building and also the panel, the airflow probably gonna reduce the ambient temperature. And yeah, that's one of the possible things that we can do in this research. So if for example, if we are using this cavity with this width, what are the effects of the ambient temperature? Does it going to reduce the ambient temperature? Does it going to reduce the heat that comes to the building envelopes? And yeah, there's a lot of things that can happen.
Can I add something to that? Yes, so sorry. So look, for the inside, the situation is that when the heat transfers inside, it's going to be trapped. For the outside, we can manipulate its reflection. So the ambient temperature increase when the radiation of the sun, the reflected radiation, hits something else. So if the goal of the self-shading facade is not to reflect it directly towards the ground, but direct the radiation up or to the sides, then we can, again, with the design, we can manipulate the reflection. And there are materials these days that reflect the radiation in a selective window, that the radiation can escape the atmosphere even. So they can be cool even when the sun is there. I think Matt Santomoris worked with the materials called selective radiative materials. So for the outdoors, there are plenty of opportunities to direct that and prevent the trapping effect, whereas for the indoors, it's very limited.
I just had a question at the back, and I'll come back to Lloyd.
Yeah, I had a couple of questions to turn to. First with Ricardo, I'm presuming that the roof material that you'd be using would be Whitehaven, because that's a bit thicker and it's a lot whiter than standard colour bond. But there are new materials that are coming out over the last 2-3 years where the surface temperature can actually be lower than the ambient temperature, because what you're doing is giving off heat at a greater rate than you're absorbing it. And so there's last 2-3 years there's been a lot of really sexy work going there and making surface temperatures lower, because your aim, as far as I can see, is to get the surface temperature of the places that are being hit directly by sunlight as to be reflecting as much as they can. So the two aspects, one's reflection, the other is the emissivity of the surface.
Yeah.
And on the concrete one, two aspects there. One of them is that I'm presuming that you're looking at using the coarse aggregates somewhere around about 50%. It might be 1/3 fresh concrete, or it might be 2/3. I'm not sure. You probably know the game better than I do, but I'm presuming if you go over around about 50% roughly, you're going to be degrading and using recycled material. You're going to be degrading the quality of the final layer. And would that be a good estimate, somewhere around about the 50% mark?
Probably in exact volume. In terms of bulk density, I'm using about 65%, which is the ACI recommended volume for 20mm coarse aggregate. So right now I'm using the same as the standard specifies for coarse aggregate. The degradation in material properties, just to kind of elaborate on that, the degradation in material properties is a result of, largely in previous literature, a result of the interface between the recycled aggregate and the new mortar. So that interface is incredibly weak. I've shown in my research that doing a particular mixing method can make that interface stronger than the other areas of the concrete. So it's one of the strongest areas in my particular concrete, and that's due to the absorption that's occurring, creating a localized, really low water to cement ratio. At this stage, I haven't seen, I've seen strength declines, but only very small strength declines, and I've been able to change mix design to alter that. That mix design hasn't been altering the quantity of the recycled aggregate, it's been altering the water to cement ratio that I'm adding here.
So you're reducing water input?
I'm reducing water input, yeah.
Have you also considered using geopolymers instead of ordinary concrete? Because that way the fresh concrete that you're putting in is actually 50% less carbon dioxide production.
So I had a friend at the university who was researching geopolymer concrete as well. And we have discussed the prospect of applying that to recycled aggregate concrete. At this stage, I think that's a full-on research area. So there's going to be probably a good 3 years of research worth to quantify multiple generations of recycling using geopolymer concrete, because you may get alkali reactions throughout the multiple generations. So there's going to be a huge kind of cascade of test results to find out what actually works. And that's a challenge with geopolymer concrete, is that applying it to the industry is going to be a bit more difficult because the range of scatter is probably going to be a lot higher.
I might.
Sorry, the third. Very
sorry, John, I have my hand up.
Sorry. I've got Ken, I've got Yaron, one more at the front, and then I think we're gonna wrap this up. So let's.
Daniel, I actually did want to get a little bit more insight from you of, especially with the carbon market mechanisms that affect a lot of international trade, and that will affect obviously a lot of the heavy structural materials. I wanted to ask you specifically about Australia, though.
Yes.
Like, where are the biggest opportunities for Australia to be able to almost make for the low embodied carbon like materials, like in this global trade, or are we too far behind?
It's a very good question. I think I would draw attention to, if we looked at structural steel as a first example, is that up until very recently, there's been a lot of scrap steel produced in Australia that's been leaving Australia. It's been purchased by all sorts of international entities, and they use that old steel they have what's called electric arc furnace technology to actually produce recycled steel. In the last month, we've actually had an announcement by our friends at Whyalla. The GFG group actually announced that they were going to refurbish their plant with an electric arc furnace, and we're going to actually procure as much scrap steel as possible from the local market. And that was a direct response to a number of things, but including the price signal that could be coming now from the safeguard mechanism. It was actually referenced in their press release. In New Zealand, we've had BlueScope Steel and the New Zealand government make an announcement of a very similar effect about a very large electric arc furnace in New Zealand as well. So I'd say Australia's not, I wouldn't describe Australia as being particularly far behind globally. I think if you look at the benchmarks that are being used in Australia for the safeguard mechanism and compare them to the EU, the European Union's, they're not orders of magnitude different. They're a little bit lower in the EU, but Australia can make up the difference. But I think the price signals are very important. So I think going forward, we've had a very tumultuous policy environment on the wholesale side for carbon in Australia over the last 10, 15 years. We have to admit that. But going forward, there are some opportunities. So I err more on the side of optimism, you know, that Australia can do better, do much better, and be globally relevant in this particular area.
Thank you.
I have two questions for Larissa, if I may.
Yes.
One is about the new NCC and if the updates would actually align with the outcomes of your research. If you think they would actually provide better thermal comfort for users for the data that you've gathered. And the other is about the health benefits of improved comfort, if there's any benefits that you can demonstrate that would actually cause reduction in less pressure on the health system.
I think definitely the new NCC will have some improvement and definitely improving the star rating, considering the Nether star rating will help not only force more considerate design for newer stock in South Australia, at least in the South Australia context, but definitely also it will help us understand better how we're using energy in the homes. And that's also, I think, just a side note, it's also having a reflection on how we're teaching building physics and all these topics we're talking about at the university level, how we are transferring our research to not only government and stakeholders, but to our students who will in the future be stakeholders. So I think just the discussion of new benchmarks is already enough for me, to be honest. I know there is a long way to go to make housing more efficient in general, not only for older Australians, but everyone. But I think what we see now in the differences from previous and the new NCC are already enough to start a discussion, which I think is more than enough. And your second question about health and if we have seen impacts. There is a lot of research already associating thermal comfort with health and well-being and improvements in not only our physiological health, but also mental health. We have been trying to get funding to research more on that, not only on housing quality, but also green spaces and neighborhood quality. Yes, and trees for sure. Yes, definitely. We did find associations between well-being in general. So when we did our research, we asked our participants how they were feeling, if they're hot or cold, and also if their health status and if they thought the environment was affecting their health and well-being. And we could see that when the temperatures were much higher or much lower, they definitely felt something was not good. And this is their self-reported health, of course. We didn't have a doctor analyze it all, but thermal comfort is very subjective. So the participant and us listening to people living in their homes more than a doctor, I think also helped us understand this correlation better in a way. Although it might not be scientific for many, by listening to what people feel in their homes is also making them think about it, making us think about it when we design new houses. So yeah, I think in a nutshell, that's what I understand. Yeah.
Thank you. That really rounds out the discussion as well. Time for one or two last questions if they're short. Otherwise, we can take them over dinner. But I did see. Sorry. One. Yeah.
My question was mostly answered by the previous question, but I will just add to extend that to will your research delve into linking the energy efficiency with the thermal comfort and the psychological well-being of older people in terms of their, for example, if they know that they're in an energy efficient home, they'll be okay with using energy to stay at a good temperature, whether it's hot or cold. Rather than being worried about how they use energy and putting their health at risk by not using the temperature control settings appropriately, even though they can.
Yes, definitely. So in our research, and we have new research on a similar topic, also understanding older adults, affordability, concern about costs of heating and cooling, energy efficiency, and so on. So it's all a mix of variables. But we have seen, because we do have very old houses, new houses, retirement villages, and all different sorts of typologies, we did find some correlation. It's significant, but not very high, depending on the housing quality and how much concern about costs is related to housing quality. And there are definitely the houses that had lower income, lower socioeconomic status definitely had higher concerns and would definitely choose not to use heating and cooling because of costs, regardless of the health impacts. And I think the target now, or the objective, is how to improve that in a way. I think that's the challenge. I think the association might be obvious. We do have the data, but now how to make houses more affordable so that you can prioritize comfort and perhaps not energy, I think is the problem. And that's something that most retirement villages and affordable housing are not really thinking about. So getting, yes, affordability, exactly. Yes. And that's something I also wanted to kind of wrap up, because we did talk a lot about energy, embodied energy and so on. But it would be also good to have a discussion about life cycle costing, because regardless of how the embodied energy improvements we might have or so on, sometimes very difficult to get this to real life and real scenarios when costs is a variable as well. And
Dimension, isn't it?
exactly.
Yes.
And I also felt like with students, because I teach embodied energy and all these topics for second year students in the university, in academia, and we always start talking about embodied energy and how important the envelope is, not only for thermal comfort, but for energy efficiency and to decrease the impact of our buildings in the environment. And the last topic is also always life cycle costing. And then when they do the calculations and compare the alternatives, students don't really understand that variable. It's the last thing we talk about. And sometimes they get to a point to say maybe the investment of a new recycled building might not be worth it in a way, or double glazing might not be worth it if you consider the life cycle costing of maintaining and installing and so on. So maybe that might be a topic for another discussion on costs and the life cycle costing of buildings. Is not only talking about the energy benefits, but also what is the cost of all that.
Absolutely. It's like you had my presenter notes to wrap up the discussion, because I had one final question for the whole panel that links back to this concept of costing. Kind of goes the other way, but as researchers, you're limited a lot by funding and where the funding goes towards your research. But in in the gist of this towards sustainable circular economy. Last question is, if you had $1 billion in funding fall on your lap to work towards a sustainable circular economy, what would be your one thing that you would prioritize in terms of the innovation research space to push that boundary forward for the built environment?
1 billion.
Or 1 billion.
1 billion. Yeah, 1 million is easy. 1 billion is hard.
Countries everywhere.
I think for me, my biggest challenge, and that's why we always have to seek funding, is to have human resources to research all this and create this database, but also get this information and translate that information to stakeholders and to government and so on. I think that's, for me, my biggest target since I started researching, is getting what we research to be actually used in real scenarios, because there is a huge gap, and we cannot deny, between academia and practice. So for me, if I had $1 billion or whatever, I would definitely invest on that, on filling that gap. Yeah.
The education aspect.
Yeah.
Can I ask a question about that? Is the $1 billion something on which I need to get a return?
Well, in this hypothetical universe, you can be the decider.
Okay. So I think if, let's assume there has to be some return, maybe not a huge one, but I think going back to Larissa's point, about, I think we've got the wrong incentive structures at the moment. When we look at buildings with 30, 40-year, time horizons and lifespans, very often the lease, if we talk about commercial buildings maybe to begin with, but we can talk about also a lot of the other leased buildings, even hospitals, private hospitals, usually stack up or are made to stack up on the basis of a 5, 10, or even 15, in some cases a 15-year lease. But as we can see, there's a mismatch between the length of that lease and the actual full life of the building. So I think those incentives direct people, and when I say people, I mean economic actors, developers and others, are channeled towards solutions that work in that reduced time frame. And so with my $1 billion, I would work to create different incentives so that those decisions that are taken based on those minimalized time horizons are actually opened up more. Because I think that's when we can start to see more balanced solutions.
Should we keep going this way?
With my $1 billion, I would first approach, because I'm sure the $1 billion would go a fair way. Every state of Australia, I think capital cities, I would like to set up an industrial practice for recycling aggregate and using it at a high standard. So classification of the aggregate, high performance mix designs, the mixes going directly from this place to site and being used. I would also categorize and catalog all pours where this is done so that we can keep track of which generations used where and then. Then we'll have a better idea of what's coming to us later on. That said, we don't need that, but I would also set up a research institution targeting future findings with recycled aggregate, looking into embodied CO2 within the recycled aggregates, looking into upcycling those recycled aggregates, and looking at reducing CO2 emissions related to cement production.
Very thought out answer.
Yeah, he has already thought about it.
Yeah, if I got billions, I think the only thing I can think about is building some kind of a living lab. So living lab is something that you can implement in the building where you have all this era of big data and you just implement all the sensors you had in the building facades. And not just in the building facades, but also in the interior part of the building. And it actually combine all the data into one database, and you can use that for future research because currently when people are trying to conduct research, they have to go to the buildings and they have to set up sensors like all these researchers in. And yeah, it doesn't really efficient in terms of time, and sometimes there are also technical issues. So when the buildings are implemented with a living lab, we can just do everything with the big data. That's it.
It's my turn. So $1 million would get me 1,000 passive houses. I would make 1,000 passive houses. I would let politicians to come there and stay there in a week, and then I would kick them out. They wouldn't be able to live in their houses anymore, so they would do something about it. Yeah.
Implementation by force.
And for the money, I will just rent them out during the Christmas, and I will return them.
What a fantastic one to end on. Round of applause for the presenters, please, everyone. Thank you so much for your time, everyone on the panel, and also for you, the audience, for being here. I've also got a list of thank yous to obviously the speakers for sharing your generous time and knowledge. It's been a fantastic discussion, and I hope we can continue it over dinner. Thank you to Uniting Communities for providing us with this wonderful venue and space. Thank you to Sebastian and the team for your photography and videography. To the crew at Troppo for the catering you are definitely about to enjoy. To all of the ASBN volunteers who make these nights possible. And to all of you, thanks again.
Thank you.
Enjoy dinner.
And one last shout out to the fantastic Marina for not only organizing everything, but also taking on MC. Everyone give a real laugh.
Thank you, Ken. Big shoes to fill. Enjoy dinner, everyone.
Thank you.
Thank you.